Hi, everybody, and welcome to this 10th week of BIOB20. And this week, we're going to talk about confidence intervals. But before doing that, I'm going to ask if there are any questions about the content that we've seen up until now, things that you'd like me to explain again, or that you'd like me to expand or to comment on. Online, you're also allowed to ask questions, of course. What about the tutorial this week? How did it go? Yeah, with the book look some tests, etc.
It was good. We had a little trouble with the wording.
Little trouble with the wording. So what was unclear?
I think for me, question number 3 or 4, where it was like how many ones see. I'm pretty sure how I coded it was correct. Like it matched what was in the file, but my number is not the same as what you had.
Okay. I'll check that. I'll check if it's a question of wording or if there is an error in the answer. Yeah, indeed. So. Sure, with pleasure. So how is this concept of the chi-square working for you guys? Do you understand how this test works, why it works, and why it's confusing, why it looks like we're using the data to make the predictions, but in reality we don't. It's called expectations, but that's really just computing the score. The score does depend on the expectation, but these expectations are not used directly in the null hypothesis. They're used only for the computation of the score. Is that kind of getting in this idea?
I mean, I think there might have been a typo, like in terms of like comparing the tutorial question and then this question.
Yeah.
There was like a typo on equations, I think.
Oh, well, yeah, sure. Yeah, then please report every typo to me. Everything is interesting for me to fix, of course. Okay, so in today's class, we're going to talk about confidence intervals, and about in particular one thing that I should have mentioned, I should emphasize much more at the moment when we started to talk about it, is that there is kind of a huge difference between accepting the null hypothesis and rejecting a null hypothesis. And of course, the difference is one is a reject, the other one is an accept. But what I mean is that when you reject the null hypothesis, you're kind of sure. Okay, so this is, you're making a statement that the null hypothesis is fundamentally incompatible with the data that you have observed, at least in the sense that you give some guarantee, let's say 99% or something percent, and you say you are that much percent sure when you reject that there is a fundamental incompatibility between the observed data and your hypothesis. So rejecting the null hypothesis is a strong statement. You say there is fundamentally an incompatibility between the data and the hypothesis. But accepting the null hypothesis is not the same. So in a way, you accept the null hypothesis, but you're not really saying that this null hypothesis is the truth. You're just saying that you did not have enough evidence to reject it. So you're kind of accepting it by default. So it's exactly the same as in the justice system. The question is, who has the burden of the proof? Everybody is innocent, unless you can prove that they're guilty. So you don't have to prove that someone is innocent. They're all innocent. They start innocent. You have to prove that they're guilty, and that's exactly the same with null hypotheses, is that they're all true, all of them, and you have to prove that they are not if you want to reject them. And so when you accept one, it's not necessarily because for sure it was true, it's just you didn't have enough evidence to be able to reject it. So why do I say this, and how does that matter in practice? We're going to give an example that'll make these things a little bit more clear. So as usual, we start with my very favorite sample, the 5 Gaussian random numbers. So here we got 5 Gaussian random numbers. And by now we're pretty familiar with all this testing tool set that we have, and we don't need to make a whole complicated scenario. We just need to say a t-test on X. And so that gives us a one sample t-test here. Very simple way now to get these tests done and to get the p-values very fast. So in that particular example, when you say t-test with one sample, there is an implicit null hypothesis, which is that the average, the expected value of the population from which you took X is 0. And so that allows you to get the null distribution. That's what we had done in week 3 or 4, I can't remember, with the proton gradients. And so you get the whole test that is done. And at the end, you have the p-value, which is there. So in that particular case, what do you guys think? Do we accept the null hypothesis? Do we reject it with a p-value of 0.36? We accept, okay? So most people would accept the null hypothesis, almost everybody actually, because that's nothing extraordinary. You have a 36.5% chance of seeing a mean that is more away from 0. So if you look at the mean of X, it's like minus 0.3 more or less, and that's not extremely far from 0. And when you have five numbers in the sample, then the expectations are that you're actually quite likely to see deviations that are bigger. You're like 36.5% chance of seeing something that's more away from 0 than that particular number, at least from the assumptions that are made in the test. Okay, so far so good. So we accept the null hypothesis that the mean is 0. But what about if I had made another hypothesis? Not that the mean is 0, but that the mean is 0.00000000001. That's not the same hypothesis. It's almost the same, of course, but that's not exactly the same. Would I accept this one as well? And you'd say, yeah, intuitively, of course. Like, you know, like if you accept that the mean is 0, you also accept that this is a tiny little bit different from 0. And one way to test this is to say that testing that the mean of X is equal to 0, that the mean of X minus, let's say 0. Plenty of 0, 1 is equal to 0 is the same as testing the fact that the mean of X is equal to that. Okay, so if we're doing that test here and we accept the null hypothesis, it means that we accept that the mean of X is equal to that number that I'm plugging here. And sure enough, you know, you can see that there's of course no difference between the p-values. The difference that I'm introducing are way too small. That's kind of intuitive, right? So still, this is not the same hypothesis. X, the mean is equal to 0, the mean is equal to that number, which is very close to 0. So we get the feeling that we do accept the null hypothesis that the mean is equal to 0, but we have to accept every hypothesis which is extremely close to it, which is exceedingly close to it. And that's kind of a given. And of course, we could say, well, it's because this is statistics and things are very, very blurred, etc. And so when we accept something that's almost identical. That makes sense. But not completely, in the sense that there are also some hypotheses that we can test, which are significantly different now, significant in the everyday sense, not in the sense of statistics. So what about testing that the population from which X is taken has a mean not of 0, but 0.1. And you can see that the p-value is 0.24, so we kind of accept it again. And now this time 0 and 0.1, they're not very the same anymore. Like these are actually numbers that we can distinguish. Of course, that depends what X is and what kind of data we're looking at. But in general, you could see that we accept not just hypotheses that are exceedingly close, but also hypotheses that are a little bit far away from each other. They can still be both accepted. So what do you guys make of this? How is it possible that we accept the null hypothesis that the expected value is 0, that we also accept the null hypothesis that the expected value is this tiny number, and that we also accept the hypothesis that the mean is 0.1. How is that possible? That we accept all these mutually exclusive conditions. Go ahead.
I think this kind of relates back to the topic of power and the ability to distinguish when alternative hypothesis is true.
Mm-hmm.
In that when you are comparing two values and they are close together, it's much harder to distinguish whether one is actually
Yeah. So what Mira is saying is that this relates to the notion of power, is that this power kind of tells you how much you can differentiate the truth from whatever is not true. And so if you have enough power, then you could differentiate 0 from, let's say, 0.1. But in the absence of that power, you kind of have to either accept both or reject both. You cannot really distinguish one from the other. That kind of relates to that idea exactly. So we also have other comments online that say that they fall under the 0.05 significance level. Yes, we said that they're compatible with the data as discussed in the video. Yes, in the sense that we don't say that we really accept the null hypothesis. That's not the way we should say it. We should say that the null hypothesis is acceptable. Okay, so 0 is acceptable, 0.00001 is acceptable, and 0.1 is also acceptable. So in that sense, accepting the null hypothesis is not a mutual acceptance, a mutually exclusive acceptance. Okay, you say, I accept it in the sense that this is acceptable to me. Like with the data that I have, this is acceptable. But something that's really important to understand is that accepting the null hypothesis and choosing the null hypothesis as the truth is not the same thing at all. And this is what's very confusing in people's mind, is that a test is not an estimation procedure. Okay, this is not an estimation procedure. This is a decision procedure. Either you're doing something with the result of the test, you're making a decision, something that you cannot undo after you've done it, but you're not doing it for estimation. And people get very confused out there in the scientific community that when they accept a null hypothesis, that mu is equal to 0, for instance, then they jump to the conclusion that they also choose that at their estimation and that they have proven that mu is equal to 0. But they have not done such a thing. They have not proven anything like that. Okay, they just have accepted that mu is equal to 0, so that makes mu equal to 0 acceptable. That's all it does. Okay, this is not the fact that it is equal to 0. It just means this is acceptable, but you have not chosen it as the true as truth. Basically, you just said that this is acceptable. Okay, so this is something that is a little, it's a little bit difficult to understand because of the vocabulary that we use. We say like to test, and then we have a null hypothesis that we accept, etc. But in reality, it's important to understand that this acceptance is not exclusive with other null hypotheses. Just because we accept one, the fact that the null hypothesis that mu is equal to 0, does not mean that you have to exclude other values. Actually, you even have to include other values. This is not possible to have a null hypothesis, at least in problems that we have, where only one value is possible. You will have a continuum of values. And so you know that for very, very, very close values to this one, you will also have to accept them. So that's important to understand. Rejection is another story. You're saying that this is incompatible, like you cannot accept it. But when you accept, this is not an exclusion. Okay, so far so good? So we haven't really spoken about this at the moment when we mentioned this notion of testing, etc., so that you guys can get the ideas clear about the procedure. But now that we focus on the interpretation, it's really important that you keep that interpretation in mind. Accepting the null hypothesis does not mean that the estimate is the value that you've chosen. You have a whole possibility of slew of hypotheses that you could have accepted. You got one, good for you, but there are others out there, and that'd be interesting to investigate what these other hypotheses are. So that's what we're going to do now with the example that we gave with this X that is here. We could be interested in, given that now we allow ourselves to have multiple hypotheses that are acceptable, well, what exactly are these hypotheses that are acceptable? What are we want the whole set of the ones that are acceptable. We'd like to see the whole range of values that we're accepting versus the one that we're not accepting. And that's what was in the video for today's lecture. So we're going to do it again because it's good fun. So when we do t-test here, we're testing the null hypothesis that the mean is equal to 0, that the expected value to be more accurate from the population is equal to 0. And when we do minus some value here, like 0.1, we're testing that the mean or the expected value of the population of X is equal to 0.1. So we're going to do that systematically. First, we're going to make a sanity check that when we go relatively far from zero, I want to go farther. When we go relatively far from zero, then the p-value is going to very low numbers here. So is the mean equal to 3? No, very unlikely to be equal to 3. And is the mean equal to -3? Also no, the p-value here starts to get quite low. So between -3 and 3, we're kind of confident that these are unlikely values for the sample that we got here. So we're going to test within the boundaries -3 to 3. What are the null hypotheses that we could accept versus the ones that we really could not or should not accept? And one way to do this is, of course, to use the for loop. That makes things relatively easy. So I'm using mu as my standard name for a variable for the average, like the expected value in the population. And I'm saying that mu goes from -3 was a good place to start, and a good place to end was 3. And we say length out is going to be 1,000 to make things relatively simple but also smooth. Then I'm going to compute the p-values of the multiple test, of the 1,000th test that I'm going to perform. So, and as usual, I like to initialize them with NA. And I remind you that the reason why I put NA is because I know that NA cannot be produced by the t-test. So if there is an NA at the end of the procedure, it's because the procedure has not run 1,000 times. Okay, like this is my internal safety check to make sure that the for loop has really gone completely and has overwritten every value that I put inside. But you could potentially initialize it with anything you like, and you don't even have to define 1,000 values to start with. So for I in 1 to 1,000, so I'm running this 1,000 times. I'm doing a t-test of x, and I'm removing mu, the ith value of mu. So I'm retesting the null hypothesis that the expected value of x is mu I when I do that. And I want the p-value. So p-value, and this I'm storing in p-vals here. And do that, it's running relatively fast. Does anyone have issues with for loops, or for loops are kind of becoming now relatively natural for everybody? Is that something that's really challenging for you to write, this kind of for loop, or for now this is going fine? I see thumbs up here. I suppose that online is probably the same, that you guys are quite confident with it now. Excellent. So we've got the p-values, we've got the values of mu, and so what we can do, of course, is to plot them on a graph, the same as we did in the video. So here we go. X is the value of mu, and then y is the value of p-vals. I want to have something relatively smooth, so I'm using type equals L, and I'm putting the grid to have a little bit of a better view of the position of everything. Okay, so we get something like this, which is pretty much the what we get in the video for today. So what does it look like that? First of all, why does it go to 1 at some point? What does it mean when the p-value is 1? Probably like getting the result is 100%. Yeah, that's kind of the idea, exactly. Yes, you're like so close to expectation that the probability of getting further away from the expectation is 1. Like you really are at the closest point to the expectation that you can imagine. And so, of course, what is the closest point to the expectation? That's the actual mean of the sample. Okay, so let's check that. So the mean of x is minus 0.29, etc. here. And so let's see that. If we put that particular value here on the graph, well, sure enough, it's exactly here. Okay, so what does that mean? It means that if someone had decided, oh, you know, I would really like to test the hypothesis that the expected value is 0.2951308, you never know. That person would say like, whoa, look at that, it's exactly that particular value here. So what, you know, like the chance that would get something that is less close to expected is 1. Like we cannot get closer than that. So that's what it means to have a p-value of 1. It means that you cannot get closer to the expected value. Wherever you go, left or right, any deviation will be more likely than what you observe right now. So that's why the curve looks like that. Goes to 1 at the value which is the closest to expectation. And then when we get on the sides here, the p-values kind of rapidly go down to 0. And then -3 and +3 here, these p-values are vanishing. They're really small. Okay, so that's the way. That's the reason why this particular graph looks like this. So why does the p-value decrease as you go down? So why, for instance, is the p-value associated with the null hypothesis that mu is equal to 1, why is it much lower than the one with the red value? What are your thoughts on that? Can it not stay high all the time? The difference with the expected result is too big. That's kind of the idea, yeah. So the more you go to the right and to the left, and so the more you're kind of assuming that the expected value would be big or would be very small or negative big, and what you have is anyway something that is around 0. So that makes it much less likely. So if you're assuming things that are extreme and then you have obtained something that's not extreme, that makes it much less likely that your hypothesis of extremism was plausible. Okay, so really, the more you go to the extremes and the less these hypotheses are supported by what you have observed. What you have observed is around 0. I'm going to actually show where they are by doing tab line v equals x. I need to plot them, for example, in blue. We're going to see where the observations are. You can see that they are there, like pretty much in the vicinity of 0 anyway. They're a little bit shifted to the left, and that's why the mean here indicated with the red line is to the left, but the values are there. So if you assume that the mean is very far away, either on the right or on the left, then of course these assumptions don't have a chance to explain reality, so that's associated with small p-values. In the end, it's always the same. There's only one location, which is the one that gets the highest p-value, and after this, the p-values decrease on both sides like that. So if you have to guess about a value, which would be the best estimate for the expected value of the population from which x is taken from, well, that would be the red line. That'd be the mean, of course. Okay, like if you have to choose just one value, that'd be the red mean. And would you be right in that case? No, you'd be wrong. We know that x is taken from a population that has average 0, like it was made by design, but because you always have these fluctuations, and it just cannot be in practice that this is the right value. And every statistician knows that a point estimator is never correct. There's just no chance that you would aim exactly at the correct value. So these point estimators, they're kind of nice in the way that, okay, they have the property that when the sample grows bigger, then they will converge to the right location, but they're also not nice in the sense that you always know that they're wrong. Like they cannot be spot on the right value. That's just not possible in a continuous world. So what do? Well, you'd like to have something that can be right sometimes, that has a chance at least of being right. And instead of giving you one value for estimation, gives you a range of values to say, like, that gives you an idea of where the value could be and also where it could not be, because like you say, it's probably within that interval, but everything that's on the left, everything that's on the right is unreasonable. That's stretching it a little bit too far. So how could we do that? Let me plot again this thing with without all the clutter. So because this here, where the p-value is 1, is our best estimate, we could say that we're going to take a line, and above the line we keep these values, and below the lines we just throw them away. So for example, I'm putting this line here. So that'd be my line that I put at a threshold of 0.05. So that line that's here would be the values that I consider acceptable. So if I work at 5% rejection, okay, everything that's on the left of that extreme point here and everything that's on the right of that point correspond to hypotheses that have a p-value below 0.05. So if my threshold is 0.05, I have rejected them. These p-values, these hypotheses are rejected for me. The only ones that I accept are the ones that are here within that interval, which is in the center. Okay, everything that's on the sides, I cannot accept because they are associated with p-values that are below 0.05. And like I said, a reject is a reject. So it means that this is not compatible with the data. So I got to be consistent and I reject these things. But that's if I work with a threshold of 0.05. I'm ready to take the risk of 5% that the null hypothesis is correct, but I reject it by mistake. So that's what we say. If I want to reduce that risk, if I don't want to work with a 5% risk, but with a 1% risk, then the set of values that I include in my set would be not the same. Okay, so if I work at 1%, it corresponds to making the bar a bit lower. So we include substantially more values in the interval. Okay, you see this, that when I lower the bar here, I make the values, the interval widen quite a lot. So why is that? So I don't want to take that much risk anymore. And so if I don't want to take that much risk, it means that I need to extend my interval a little bit more in order to compensate for the fact that I don't want to take as much risk as with the 95% confidence interval here. Okay, so the lower is your threshold here, the wider is your interval. And the threshold, which is in red here, is called a 95% confidence interval. That's the definition here. And the interval, which is in blue, is called a 99% confidence interval. All right, so far so good? So what does it mean 95% confidence interval and 99% confidence interval? So the first question is confidence interval for what and why? So here we mean 99 or 95% confidence interval for the parameter that we made vary in this kind of plot. So what was the parameter that we changed here on the x-axis? It's mu. Okay. So what is mu here in that case? That is the average of the population. That's the expected value. So you could say here is mu or the expected value of the population. So we are making an estimation for the expected value of the population, and we find a whole bunch of values in which we hope that the true expected value of the population sits within these intervals. So question for you guys, does the true value here belong to the red interval? Does it belong to the blue interval? So does the true value of mu belong to the red interval? What do you guys say? Someone says yes. Marco says yes. Does it? So question is, what is the true value of mu? It is 0. And the reason why this is 0 is because I have at the very beginning of the session, I have said that x is taken here with our norm n equals 5. So that means that the mean is by definition 0 if you don't specify it. Okay, so the mean was 0. Of course, in practice, you take only 5 numbers, so there are fluctuations. So Marco says that this is 100% sure, not even 95%. Yeah, exactly. So 0 is in this interval. That's a fact. This is not a probability or something like this. Like in this case, it is present in the interval. That's for sure. Is it present in the blue interval, in the 99% confidence interval? Yes. Okay. Like, of course, every value in the red interval is in the blue interval, so it is present. It would not be present in a, for example, 20% confidence interval. Okay, so if you want to have a 20% confidence interval, the line would be here, and you could see that it'd be a relatively tiny confidence interval, but it would not contain the value of 0. And of course, you can't have your cake and eat it. You cannot just have a tiny interval for estimating your parameter and always have your parameter in it. So if you want to have a good chance of hitting your parameter, you need to make that interval bigger. And so that's why a 20% confidence interval, no one uses it, because the chances of them even containing the proper value is too small. But 95%, 99% of very frequent choices, people are comfortable kind of having intervals that are maybe relatively long, but at least they got a good idea that the value that they're looking for is within that interval here. Okay, so that's a bit of a choice, whether you have a 99% confidence interval or 95 or anything like this. And always the trade-off is if you increase the confidence, by going from 95 to 99, you have to make the interval wider. You cannot just get anything for free. So what would be the way to get an interval that is getting more accurate without sacrificing, by keeping the same confidence, let's say 95%, and finding a way to make the interval shrink? How could you do that? Increase sample size, says Marco. Okay, does that make sense for everybody? That if you increase the sample size, then your interval would get progressively shorter. So why is that? Let's think about the mean, for instance. How sure are you about the position of the mean with a sample of size 2 versus a sample of size 1,000,000? Like you're much more sure of where the mean are with a sample of size 1,000,000. Like the fluctuations are actually much smaller over 1,000,000 than over 2. Okay, the mean will be closer to 0. Indeed, the observed mean will be much closer to whatever the population mean is if your sample size grows bigger. So that's going to actually shift your interval closer to 0. That's the first thing. Like all your values are going to get closer to 0, but also that's going to make this plot go very, very thin like that. Okay, it's going to be very, very peaky. So why is that? Is because as the sample size grows bigger, then the uncertainty about the position of the mean gets shorter, and that's reflected in the t-test. Like that's automatically compensated for in the t-test. So that would make your plot peakier and peakier, so that your interval would get like smaller and smaller. At the end, when you have an extremely huge sample, then you'd get a tiny interval even at 95% confidence. But the only way you can get there is by having extremely large samples. So that's why getting more data is, of course, always better, at least for statisticians, in the sense that it makes the intervals for this confidence estimation, for this confidence interval estimations, much smaller. So you have more information about where the parameters of interest are. Okay, makes sense for everybody? Good. So now I've been talking very loosely to say 95% confidence interval, 99% confidence interval, but what does that mean, 99%, 95%? For what exactly? What do you guys think? Any idea what that could stand for when we say this is a 95% confidence interval? 95% of what? For what? So the answer is that it's a 95% chance that the value of interest is in the interval. But we have to be extremely careful about what this means. The phrasing is really everything in that case. So, question, is there a 95% chance that 0 is in the red interval? What do you guys say? Yes. The answer is no. Like nobody agrees on this. Like there's no school of statistics, or there's no teacher that would agree with the fact that there is a 95% chance that 0 is in the red interval. Everybody agrees that it is in the red interval, right? So like that's a fact. Now it's a fact. It's too late. Like that has happened, and we can see it, and there's no more uncertainty about this. For a fixed interval, the chance is either 0 or 1. So That's another way of phrasing it. Margot suggests that the chance is either 0 or 1. Some people say this is not even a chance, in the sense that the red interval, it exists now. This is not random. It's a real thing in the real world. And 0 is also a thing in the real world, and none of them is random. They're real things. And so you cannot even give a probability that 0 is in the red interval. It either is or it isn't, but it does not even have a probability. So this is what Fisher said. The guy who invented confidence intervals invented them precisely for that reason, because he did not feel comfortable giving a probability that mu is anything at all. It says if you do that, if you say that there is a probability that mu is in the red interval here, then you're saying that mu is a random variable. Then you're saying that if it's a random variable, there's a random process that generates mu, and that this process can repeat over in time. And Fisher said, no, there are many things that are not like that. Like they're the way they are. There's just one, and that's it. What is the probability that that my height is 1.80 meters? For Fisher, it doesn't exist. There's only one Guillaume, and either his height is 1.80 meters or it's not. There's no probability. We cannot rerun the whole thing multiple times. You cannot run a random experiment with it. Therefore, you cannot even find a probability with it. So either 0, mu was 0, or it wasn't. But this was not random. This was just a unique event. And as a unique event, as every unique event, it does not have a probability. So that's maybe not so important. At least in my opinion, that's not so important. Some people really are picky about this thing. But what is important to understand is that it is not true. It is not true that there is a 95% chance that 0 is in the red interval. Okay, so once the interval is in existence, then this is not true that there's a 95% chance that it contains the parameter of interest. In that case, we know the parameter of interest. We know it's 0, so we can tell yes or no. But when we don't know the parameter of interest, this is still not true. And in the tutorial, you will see an example. I start at the end, a question maybe 11 or 12, something like that. That will kind of show you why you cannot say that if you have a given confidence interval, there is a 95% chance that it contains the target value. It's just not true at all. Like this is an example in the tutorial where you see that it's very far from that. So what does it mean then? All this to say, what does it mean that this is a 95% confidence interval? It means that the procedure that was used to create it, the process, succeeds 95% of the time. Right? It doesn't mean that that particular interval here has a 95% chance of being correct. Okay, it says that when I apply the process all the time of computing these 95% confidence intervals, 95% of the time I will be right. They will contain my value of interest, the target value. Okay, so it's the same thing as saying there is a company where 95% of the customers are satisfied. Doesn't mean that if you take this particular customer here, there is a 95% chance that that person is satisfied. Okay, if you know nothing at all about this person, yes, okay, 95%. But if you see that this person is raging and then is bumping their head and then is destroying the shop, or you say I'm not 100% sure. I'm not 95% sure that this person is a satisfied customer. You may have more information about that particular either interval or that particular value, etc., which is not taken into account. So the process of computing the confidence interval really is always the same, no matter what you know about mu, no matter what you know about the confidence interval. And the only thing it does is guarantee that if you follow the procedure all the time, you will be right 95% of the time. But it does not say that one particular example there has a 95% chance of being correct. That's not what it says. Actually, it can be quite far, depending on the other information that you have. So let's focus now a little bit about this idea that we have a process that has 95% chance of containing the correct value. So why is that so? Let's think about it. So no matter what happens, no matter what produced the sample X, there is one truth. We assume that. Okay, we don't know the mean really that was used, but there's one of the, like there's just one among all the possible values that was the true one. Okay, so what was the chance? What is the chance that this value is present in our confidence interval at 95%? All the values divided by the total number of values. Yeah, all the values in the confidence interval divided by the total number of values. It's much more tautological than that. Okay, like this. I mean, the answer is just so tautological that it feels like I'm going to make a trick. Like I wish I were being able to make magic tricks, but unfortunately I cannot. All I can do is statistics, and so it will look like I'm going to make a trick with your mind, but there's no trick. It's just that if you understand the definition, then it will suddenly make sense to you, and you won't even believe how tautological it is. So yeah, think about it. One of these values out there on the x-axis is the correct one. There's just one that's the correct one, but we don't know it. What is the chance that this is in the interval? Well, I'm going to test it. One of these null hypotheses, because I'm testing them all. One of them is this correct value. What's the chance that I reject it? So because I'm testing all the values, that's my approach. Like I'm saying, I'm going systematic. I put all the values between minus infinity and plus infinity on the line, and I'm testing them all. I'm making a null hypothesis out of each and every one of them. And one of them corresponds to exactly the correct value. It's there, I test it. And because I'm testing them all, at some point I'm going to test this one. And when I test this one, what's the chance that this is in the interval? Like what's the chance that I reject it? It's 5%. I've chosen that's yeah. So it's completely tautological. It just means that this one value, which is the only one I care about, well, I have 5% chance of rejecting it, but also have 95% chance of accepting it. So there is a 95% chance that this is in the set of all the hypotheses I've accepted. It's completely tautological. Right, but it's really hurting to understand why that makes sense. But that's it. We have, with that very simple rational, explain why there is a 95% chance that the interval contains the correct value. Okay, that's the only value that we care about. It's just one that we care about. Of course, we have to integrate many more just so that the rule continues to apply. But the rational is only about this one value that we care about. So a 95% confidence interval says that no matter what the true value is, for every true values, doesn't matter which it is, I always have a 95% chance of having it in the set, just because of my rule, which is my set is every value that has a p-value above 0.05. Right? So my set is all the values, all the null hypotheses that pass my 5% rejection rate. That is sufficient to guarantee that you have a 95% chance of having the true value within your set. It's an extremely rational and formal argument, but once you get it, it's an extremely powerful one. Okay? And so observe the rational of Fisher here. There was never, no, go ahead. Tautological, what does it mean? A tautology is something that is obvious. For example, like before he was dead, he was still alive. That's a tautological statement. It's kind of so obvious because it's circular. And so this rational of Fisher, I qualified it as tautological because, yeah, things are in the set because they are in the set. And at the end, we're a little bit saying that, like the values are. Like the reason why there is a 95% chance that the null hypothesis, that the true value is in the set is because there is a 95% chance that we choose it. That's really like really what it is in the end. But what's important in this rationale is that we have never made the hypothesis that this value was a random variable. Okay, which we just the only thing we had to do for this rationale to apply is to assume that there was only one truth. And so that's still a statement that we had to make, but that's it. Like we say, there is only one truth, and we're testing all the possibilities, the true and the false, etc. We're testing them all of them. And so the fact that there is only one truth, and the fact that we have a test that is properly calibrated, that at the moment when I'm going to test this particular hypothesis, which happens to be the truth, then I know that I have a 95% chance of accepting it. That's actually the only thing I know about my test. Okay, I don't know the power, I don't know anything, but I know that my test guarantees that. So you can nicely combine the idea of the test with the idea of interval estimation. They really combine very well, provided you understand that accepting the null hypothesis just means that this hypothesis is acceptable. Doesn't mean that this is the truth. Okay, so you don't accept only one hypothesis, you accept a whole bunch of them. And what you know is that there's a 95% chance that yours is in there just because of your rule. If you change your rule, if you modify it to something like that, then you don't have any more of these guarantees. So you have to be very careful that the guarantees apply before you even start doing anything. And this is really the whole philosophy of the frequentist approach, the Fisher approach, is that you have to be able to compute the null distribution before you start collecting the data. And this 95% confidence that you get it before you have collected the data at all, because it's the confidence of the procedure. This is not the confidence of the result. Okay, so that's really important that you understand. It can be sometimes a little bit tricky and also quite confusing, like, you know, but every time you have something that says works 95% of the time, yeah, that's a confidence interval, that's good. Or, you know, like all these products that work 95% of the time, it's fine. Doesn't mean that when you have one particular example and you have the result, that there's a 95% chance that this one has worked. You may have more information about it or less. Well, less is kind of hard. Okay, so this is a very nice construction by Fisher that guarantees that if you just follow that protocol, 95% of the time you're going to be sure that your value is within that interval, or 99% or something like that. And that is good enough. Okay, that says that when you give these intervals, these 95 or 99% confidence intervals, they tell you something about the position of the parameter of interest, the central value, but also where it could have been, where it probably is. Okay, so far so good? Any questions about the interpretation of confidence intervals?
If we have the result, so like the result is either wrong or correct or not, but 95% of the times it will be correct.
Yes.
95% of the time it will be wrong.
Yeah, exactly. So once you have the result is either correct or not correct. According to Fisher, it does not even have a probability, but 95% of those results, for someone who is a professional statistician who does these things all the time and follows very strictly the protocol, 95% of the prediction of that person will be correct and 5% will not. Yes.
So, like, counting this like logic, if I'm an experimenter, and I know by the end of my experiment, I'm gonna have to do a test to like check for the p-value. And I'll just make like a graph like this and find the confidence intervals, and then if whatever results, I know my result is to change like negative x and positive x. So I know, and I know doing this graph, I know that my x has to be below this value. Can you just like have that, and then whenever he does the experiment, it checks it, and it's like, okay, well, this is above my expected results. I can just say I accept the null to go through the process.
So your question is, why don't we make this plot with the p-values and get the intervals all the time?
Yeah.
Why do we make the test instead? Well, I agree with you. I think we should do these confidence intervals all the time. I'll explain to you in a second why. And thanks for giving me the opportunity to explain that. There's one more comment in the chat though. I don't quite understand what do you mean by 95% chance that the true value is in the set. Okay, so I'm going to explain that because it's so important. And I mean, it's so easy that we don't understand it, but the problem, like I said, it's so tautological that it feels like we don't get it. So we're making a procedure in which we want to either include values or exclude values. And that procedure is the following. We make a hypothesis that mu is equal to that particular value. And we include that value in our set if the p-value of the test that's associated with the hypothesis is above 0.05. And we exclude that value if the p-value is below 0.05. So it's the procedure. That's how you define a confidence interval. So that will make an interval, but in reality, that is a set. An interval is just a set of numbers. So you keep doing that procedure for all the possible numbers, and at one point you hit exactly the right one, the one that is the truth. Well, because this one is the truth, when you test the truth with a statistical test, you have an exactly 95% chance of accepting it. And because the rule is you put the number in the set if you accept the null hypothesis, well, you have a 95% chance of having the truth in your set. It's as simple as that. But you have to understand that what you're calibrating is the method. It's like you're really setting a protocol to always do the same thing. And that's why it works, because you calibrate the protocol. So now I'm going to go back to Heider's comment, which is I have to do a test. Why don't I do it instead of the test? I'm doing all the possible tests, get that value here, and then return a confidence interval instead. That's an amazing question. Think about it. So 0, we said, is in the red interval, in the 95% confidence interval. What does it say about the p-value? What does it say about the p-value of the null hypothesis that mu is 0? It's higher than 0.05, exactly. That's exactly what it says. And if it's higher than 0.05, it means that you accept the null hypothesis. So in reality, when you have a confidence interval, you have more information than a statistical test. You have the statistical test for pretty much all these values here, which are in the red region. You know that they all have been accepted. So if someone gives you a confidence interval here and 0 is in the confidence interval, it means that you have accepted the null hypothesis that mu is 0. Imagine a situation where 0 is not in the confidence interval. I can draw it actually for just to make it clear. So here mean is equal to, let's say, 5, something like this. So the values of x are like this. And if I do again my little trick, I'm going from, let's say, 0 to 10, and I'm going to do the t-test again. Up. And when I plot, okay, 0 is clearly not in the confidence interval at 95% or even 99%. Okay, you see it, like the confidence interval is more or less from 3 to 6, something like that. So 0 is not in the confidence interval. What does that mean about 0 as a null hypothesis? Yeah, it's rejected. You know, it's rejected at 5%. You don't know the p-value though. Okay, you just know it's below 0.05. Obviously, I think it's also below 0.01, but the only way to know it is by asking whether it is in a 99% confidence interval, and it is not. So a little bit where I'm going with this is that people are underusing confidence interval a lot, in the sense that you have more information than in a test, for sure, and you have like all the information that's in the test and more, because you're also giving other values that could have been accepted, not just one, and you also give an estimation of mu. Right? When you reject a null hypothesis, just say, nah, it's not that. Okay, but what is it? Maybe you could tell me, you know? And so people just give you a tiny p-value, like 10 to the minus 200, saying, yeah, it's not 0. And what is it? So when you give a confidence interval, you're saying it's not, here you say it's not 0, but it's between 3 and 6. That's a much, much more interesting information to say that this is not 0. So you kind of make more out of your statistical test when you give a confidence interval. Like you're saying, I reject 0, it's not in my confidence interval, and I'm telling you that the approximate value is approximately 5, and I'm saying you that anywhere between 3 and 6 is a go at 95% confidence interval. This is way more information than a statistical test. And that's what people should do. So why do they not do this? I'm not quite sure. Like the way I learned statistics, like it was approximately 20 years ago, a little bit more, is that we were doing confidence intervals first. So before learning the test, we were doing confidence intervals, and they were teaching us if 0 is in the confidence interval, it means that you accept a null. If it's not in the confidence interval, you reject a null. The reason had to do with the calculations, that we had the formulas to compute the confidence intervals, and we didn't really care to make the test per se. So it was much more frequent at the time to compute the confidence interval and then to reject when 0 was outside and to accept when 0 was inside. At some point along the way, things got a little bit different in the sense that people got very interested in p-values. And I guess my idea, but I'm not quite sure, is that the reason why they were so popular is because when you give a 95% confidence interval, you're kind of forcing people to accept your 5% risk. And they say, I don't like it. I would like a 99% confidence interval instead. Problem is that the article is written, they cannot just ask you and write to you, dear Dr. So-and-so, can you please give me the 99% confidence interval because I'm not too sure. That's kind of a little bit too much. So you just give the p-value and people are either free to accept it or say, no, like for me, that's an acceptable risk, or for me, that's not an acceptable risk. With confidence intervals, you're forcing your choice of a risk on the reader. And I think that this is the reason why people kind of preferred to not force the risk on the reader and then give the p-value instead. But the cost, in my opinion, is not worth the benefit, because now you have removed all the information about the value of mu and about the acceptable values. You have just focused on the one value that you reject, which is 0, for instance. Okay, that's a matter of opinion. This thing is not really scientific, and this is more like sociology of science more than science itself. Yes.
So like, in terms of like, let's say like I see a paper, they gave me their confidence interval, and I want to replicate. I don't get their exact like result, but I get like outside their confidence, so I can also reject. Is that like usage of the confidence interval?
So when in the paper you get a confidence interval, and when you want to replicate it, you get a different result. You mean replicate it with their data or with your data?
Well, like let's say like they you replicate using their procedure.
Yeah.
You get X value. In their experiment, their X value is outside the confidence interval, so you reject it.
Yeah.
In their experiment, you get a different X value.
Yeah.
But it's also outside the confidence interval, so you can also reject it.
Yeah.
Does that mean you can like that experiment successfully replicate in that sense?
Yes. So if X in an original paper is outside the confidence interval, 0 is outside the confidence interval, and then when you replicate it, it's the same as well. Does that count as a replication? Yes. Yes. Most people would say yes, indeed. In that case, the results have been replicated more or less. So that's a very important point here. The fact that there is kind of an overlap, a huge overlap between statistical tests and confidence interval. And of course, because confidence intervals are based on tests, and I kind of feel that that's really the way that Fisher intended them to work, as confidence intervals, not as tests so much. And this overemphasis on tests is kind of, making the party a little bit less fun. So let's give some more examples of how this works in practice. Now that we've got a good understanding of how to interpret them, what the theory around them looks, let's give some other examples of how they can be useful. And I'm going to go back to my very favorite example. I'm going to define a y that is equal to b or norm n equals 5 here. So I've got my sample x, I've got my sample y, and remember that I can do a t-test, x and y. So now I'm testing whether x and y have got the same mean, or whether they're really overlapping like this, or whether they have been shifted a little bit. And the one thing that I forgot to mention, I'm going to do now. So if I do t-test with only x, I see that there's the degrees of freedom, etc. The value of the statistic, we don't really care. The p-value is something that we're a bit more interested in. But, and that's very nice, we have here the 95% confidence interval. That is really super nice. Is that this 3 to 6, well, that's the values that we see here. The way we computed them is the complicated way. As usual, in the beginning, we always use the complicated approach, but then we discover that OR is much friendlier than we anticipated. So anyway, when you do a test, the confidence interval is there. We're just not watching, but it was there all the time. So not returning the confidence interval when you do a test is a matter of choice. Like, it's not more work to do the confidence interval. In reality, it's always there, given by OR. When you look at the manual of t-test, you could see that you have the alternative is like one-sided, two-sided, etc. You also have conf level, and the default is 0.95. So if you want a 99% confidence interval, you'd say conf level equals 0.99. And now you see that you have a 99% confidence interval that goes from 2 to 7. And so that's about it, 2 here to 7. So you just have to say how much you want your confidence interval to be, and then you get it for free. It's not more work to get the confidence interval or to get the t-test or a test. So now let's go back to what we were starting to do, which is if we do the test of x versus y now. So we are rejecting the null hypothesis very strongly, and we can again ask the same type of question, which is what are the hypotheses that I would accept? So let's go ahead. We're doing the same kind of thing. We're going to say that I'm going to shift a little bit x and y. I'm going to say, for example, that I'm shifting y to the left or to the right. I could say, for example, that I'm testing x versus y plus 1. So x is at the same position, and actually x is on the right and y is on the left. And I'm going to kind of bring x slowly toward y. And in principle, I should see the p-value increase here. Okay, like the p-values keep increasing as I'm putting them together. And at some point, around 5 here, this is an accept. So I'm kind of measuring with that method how much I need to slide y on the x-axis so that I can make it coincide with x. And that will again give me a set of values that I will accept, meaning like once I shift x or y so much, then the two means are not distinguishable, and the values that I reject, say, no, I haven't pushed enough, and so the values are still very different from each other. So this method that we were using with one sample, it works perfectly fine with two samples. So we're going to do it one more time with that method. So again, we're using the same things. We're going to say that mu is going to be all the numbers from 0 to 10, and we're taking 1,000 of them. And now the for loop is going to be slightly different, but on the same topic here, pretty much, which is instead of having x minus mu is going to be y plus mu. Okay, I'm increasing the value of y, so it's going to be x, and I'm testing y plus mu. So I'm kind of shifting y toward x, and when I do 10, then it's going to go beyond to pass x, and I'm collecting the p-values here. So I do this, and in principle, when I do that, I can plot the result up, and I get my answer, something like that. Okay, it's not exactly the same result as before. It looks a little bit the same as the one that was just on screen before, but it's not exactly the same. So if I do now AB line equals AB line equals H 0.05, I got the range here, which is there. So it goes like from 2.5 to, let's say, 5.5, something like this time. And that gives me now a range of values for the difference between these two samples. So it's exactly the same logic. In reality, we're not stuck with using t-tests and using one sample. We can actually use multiple samples and not necessarily the t-test. This whole procedure works all the time, as long as you have a way to say, that's my null hypothesis. I have a test that allows me to get a p-value, then you can compute a confidence interval. That will work. So that's the confidence interval that is there. And of course, sure enough, when I do t-test and I say x, y, well, you could see that I got the 95% confidence there. It was there all along. And so this time it's measuring not the whether the mean of x is 0, it's measuring whether the difference between the two samples is 0. And as you can see, because it's going between 2.74 to 5.79, 0 is not in sight. What does it mean for the means of x and y? So the confidence interval here does not contain 0. It goes from 2.7 to 5.8. And so Dana says it means that the means are significantly different. That's exactly what it means. That's one and the same thing. To say like this interval here given by t-test contains 0. If it does, it means that you would accept the null hypothesis that they have the same mean. If it's not in this set, it means you reject at 5%. You reject at 5% the hypothesis that they have the same mean. That's one and the same thing. Okay, there's just another way of saying it. One way you say, I tested it and I got a p-value of that, and the other one says, I've tested all the hypotheses and it had a p-value that was below 0.05. And then it was not in the hypothesis that I kept. You're saying the same thing twice, except that you're really taking very different approaches to say that. So when the confidence interval here contains 0, it means that it's believable that the two samples are very much in line with each other. When that null hypothesis, confidence interval does not contain 0, it means that this is not plausible. They are shifted. You have enough evidence already to know that their means are not identical and they're shifted with respect to one another. Okay, so that's a very powerful concept, confidence intervals. They kind of summarize pretty much everything we've seen together about statistical tests. Quite a nice one. We're going to see again that we can actually change the confidence level. So you say conf level equals 0.99, and then you get another confidence interval here, which is of course wider, but it still does not contain 0 because the p-value is below 0.01. Okay, so it all comes together in the end, these concepts. They were all nicely laid for us to link testing with estimation, and with not just estimation, but interval estimation. So one thing that's quite nice, it's pretty nice to understand, is that you have here, when you do a t-test, okay, you got the t and the p-value, etc., but who cares? The most important information is actually in the confidence interval because it tells you what's the difference between the two samples. Like, of course, you can just measure the difference in the mean and everybody can do that, but we know that this is not correct. Like the chance that it be exactly the correct value is 0. But you get a range of plausible values. Say like anything between 2 and 6.5 is a go, at least a 99% chance. Okay, so instead of focusing on whether they have the same mean, which is not even defined, now we're talking about the effect that you can measure statistically. You know, how confident are you that they're different, and what is the value of that difference? So now we're talking about something that is measurable biologically, instead of just saying it's not the same. Like you say, the difference is that much. I think of differences in salary, difference in size, or something like this. You know, all these questions about equity, etc. People say they don't have the same salary. Yeah, but how different are they? You know, we're talking of a difference of $1 per 10 years or a difference of $2,000 per month. So all these things like having strict equity, etc. Of course, that's important, but we need to be able to talk about the values, the differences of the values, not just whether it's the same or not. Biologically, it's the same. Okay, something protects you against COVID-19 or cancer, something like this, because it's better than the placebo. Sure, how much better is it than the placebo? How much does it protect you against cancer? These are things we want to know. And just telling it's better than randoms, yeah, sure, how much better is it? So these are really important things to bear in mind, that the confidence intervals that are given for free in the t-test, well, they are kind of giving you more out of your inference than just doing the test. So the t-test is one possibility, and as we've seen in the group work, it doesn't have to be the t-test. We can actually use another test. Okay. So what about, instead of doing the t-test, here in my for loop, I'm going to do the Wilcoxon test. After all, that can work. That's also a test that you can do on two samples. And it's, again, pretty much doing the same thing, which is to measure whether they're exactly aligned with each other or whether there is a shift between the two. So we could do the same here with a Wilcox test. That's going to work as well. So let's see what we get. So now we plot the result, and we see something like this, which is all blocky. I think that this is something that some of you have noticed before. And we've got the line which is there here. So first question, why is it blocky? That's something that we were discussing in class here for those who were doing the group activity in the room. And that's because the Wilcoxon test is based on the ranks. It's not based on the values that you have. So when you have two samples that are, for example, completely separated, like, you know, the X sample is completely on the left, the Y sample is completely on the right. So all the ranks here is 1, 2, 3, 4, 5, and here is 6, 7, 8, 9, 10. If I move this a little bit, the ranks don't change at all. Okay, like it's still 1, 2, 3, 4, 5, and 6, 7, 8, 9, 10. Until there's the first cross here, where the leftmost value here and the rightmost value here cross. There's no change at all of the ranks. And you can see that this is why these lines here, at some point, they get flat and they never change anymore. That's the extreme value of the statistic. It cannot get higher. And so the p-values don't change at all. Like, you can put these guys as far apart as you want. The ranks don't change, and therefore the p-values are constant. And so the measurement of these p-values as you make them go away from each other do not change. So in one case, they're separating like this. When you go to the other extreme of that plot, they have crossed completely, and they're actually separating like this in the other direction. But either way, you get a flat line with a p-value that does not go below a certain threshold. And that's because of the nature of the test we're using. So we're seeing that depending on the test we use, of course, we're going to get a different profile of p-values. And of course, we're going to get consequently different confidence intervals. So here, these are the p-values that we get. They're jumpy and blocky because they change only when you have two values that cross each other. And so, like, the number of crosses that can happen when you have 5 values that kind of go along each other like this, every time there's a jump is because 2 values have switched side. And that gives a maximum around there for a shift of 4 point something, 4.2. And when the shift is too big or too small, then the p-value does not go to 0, it goes to the minimum which is possible with these values here. And we got like jumpy changes in the p-values every time 2 values cross. Now, using that, we can recover the values that are there and there. And that would be our 95% confidence interval. So let's see what they are. We're going to try and recover them. So how do I do this? I could say which p-vals is greater than or equal to 0.05. That's all the indices of the p-values here in that graph, which are above the red line. So if I plot them, then if I print them, I see that this is everything from position 276 here, that must be this one, to position 665, that must be this one here. So what values do they correspond for x? So that's x is mu here, and so that's 276. So that's 2.75 to 665. Here. So from 275 to 664. Okay, that corresponds to what we see here. That's reasonable for 275 and 664 as well here. So that's my confidence interval with the Wilcoxon test. Now let's see what it was again with the t-test. T-test, so xy. And if I do nothing, I get the 95% confidence interval for free. So it was 2.74 to 5.79. So these two values here on the left are pretty much the same, but these ones are quite different. Okay, so the t-test confidence interval is quite different from the Wilcoxon test confidence interval. Now, which is the right one? Which is the correct confidence interval then? What do you guys think? They can't both be right because they're different. So which is the correct one?
I don't think the samples usually the data you get is just what that's on.
So does it depend on the sample? Yeah, of course. You use different x, different y, then you're going to get different results, of course. And so sometimes one of them is going to be shorter, the other one's going to be bigger. But still, do you think that on some samples the Wilcoxon confidence interval is correct and the t-test is not? So what would that even mean? Would the Wilcoxon test be better for smaller samples? Better in what sense? It's a very interesting idea, but better in what sense? So first of all, are they really both confidence intervals? Are they both 95% confidence interval or not? Or is one of them not a 95% confidence interval? Marco says yes, they are both confidence intervals, both 95% confidence intervals. Yes, they are. Okay, they are based on this idea that you have a 95% chance of having your true value inside. That's it, like both of them have this property of being a confidence interval. Yes, both of them are. It doesn't mean that they, that one of them will always contain and they all will never contain, of course. But they are based on different tests. Exactly, they are based on different tests. And so what does it change? And why would you choose one or the other? Because again, like the same as when you choose between a t-test and a Wilcoxon test, when you do a test, when you do confidence intervals, you can use one or the other. Or if you have another test in mind, you can use another way of computing the confidence intervals. So how does that change and why does that matter? And if one of them is wrong, which is it? So what makes the confidence interval? I like this plot here because it reminds us that in the end, it's the statistic. It all boils down to the statistic. The statistic is really the one score that we need. We have the null distribution. From this null distribution, we compute the p-values. And what we see here in that particular plot is that when the statistic varies in a blocky fashion, then the p-values also vary in a blocky fashion. So the question that you have to ask yourself is, does the distribution of the statistic apply to your case? Is this actually a case that applies? And so let's think about the Wilcoxon test. Is it applicable here in this situation? Are all the assumptions that we needed to compute the null distribution of the statistic, are they all satisfied in the case that we have here? I think they are, because we had smallish sample, it's fine with the Wilcoxon test, it works okay. And we were really considering that they were from exactly the same distribution, but with just a shift, okay? And that distribution happened to be the Gaussian with standard deviation 1. So one of them was not stretched or compressed compared to the other. So yes, the assumptions of the Wilcoxon test were satisfied. And we also have tested only differences that were a shift relative to each other. So that very much applies. What about those of the t-tests? Like, were we allowed, in a sense, to do a t-test in this particular case or not? So samples are quite small, 5 and 5. That's usually too small for the central limit theorem to apply. But can we apply the t-test in that case or not? Do you guys remember? on this particular case with two sets of 5 Gaussian numbers, it's perfectly fine to apply the t-test. Okay, if the data is already Gaussian, then it's already Gaussian. The only reason why you need the central limit theorem is to make the mean Gaussian. But if your data starts by being Gaussian, then the mean is already Gaussian, and a sample test of 2 is just good enough. Okay, as long as you can estimate the standard deviation, and you need two points for that, then it's good enough. So that's the answer. They're both applicable. Actually, they're both fine. But one of them happens to produce wider confidence intervals than the other. So why is that? It's because the distribution of the score is not the same. Right? And so that the fluctuations of the score are a little bit less strong with the t-test than with the Wilcoxon test, because it is making better use of the assumption that the data is Gaussian. You know, it's like it is a more restrictive test, but in the case that this restriction applies, then it's actually using this information to kind of make a smaller confidence interval. So that's kind of a nice boost, you know, like you have a confidence interval that's shorter and that still guarantees that you have 95% chance of having your value of interest inside when you take the shorter one, of course, like, because you're more precise, you're more accurate.
So what if my mu is like 6?
Mm-hmm.
But like, so like in the t-test, it's outside the confidence.
Yeah. What if your mu is 6? Yeah.
What if my mu is 6? And the t-test,
yeah.
outside.
Yeah. In that case, well, you lost. if you had the t-test confidence interval, then you got it wrong. Then you lost. But it's not about one case where you're wrong. Okay, the statistics that we're talking about. You just want to be right 95% of the time. I like this saying from a statistician. Who is it again? Maybe it was Nate Silver or something like this, who said, okay, you predict you'd be right 80% of the time and you're right all the time while you're wrong. So that's exactly the way statisticians think. So say, if you say you're going to be right 80% of the time, well, you better be wrong 20% of the time, otherwise you're lying. And so that's exactly the idea here, is that on some of them you're gonna be wrong. You have to be wrong, otherwise you're miscalibrated. And so sometimes you're gonna win, sometimes you're gonna lose, but what matters is that 95% of the time you win and 5% of the time you lose. And that's going to be true for both in both cases, for both the t-test and the Wilcoxon test, but they're not going to be the same win and loses. Okay, so sometimes the Wilcoxon test is going to win and the t-test is going to lose, and vice versa.
So just to like clarify, when we say being right or being, like if we're in that 95% confidence interval, that means we accept it, and if we're outside that 95, that means we reject it.
It depends. So if you're within the 95% confidence interval, all the values in that you accept them as null hypothesis. If you had used any of these as null hypothesis, you'd have accepted it.
In the context of like comparing like experimental results or random chance, you would know that like that's you would be able to say I accept or reject based on those stuff.
Yeah, if you're now comparing experimental results to random chance, yes. Like all the ones that are in the confidence interval, you'd say those are the ones that I cannot distinguish from randomness, let's say, but everything that's outside the confidence interval, then I can distinguish. All right, so basically, to conclude, the confidence intervals, they still do depend on assumptions. That's what I wanted to mention, is that you still make assumptions to make an interval. You believe some things about the world. You say that this is Gaussian, for instance, that there is random independent sampling, for instance. Like it could be anything. There are many possible assumptions that you're putting inside the confidence intervals. And if these assumptions are not correct, then your interval is false. Like you don't have a 95% chance of having the value of interest inside. Okay? So if these hypotheses are correct, then that's okay. Your interval is nicely calibrated. And if you can make more assumptions about the world, then you can find a test that uses these assumptions and that will make smaller intervals. So kind of making your information a bit crisper and more on target. But if these assumptions are false, then you're going to make more mistakes because of that, because you're kind of believing that the reality is Gaussian or something like this when it's not. So that's all I wanted to tell you about confidence intervals. You will see now in the tutorial how to use that. We're going to go back to the very first tutorial, the one about the vaccines, and we will use neither the t-test nor the Wilcoxon test, but yet another way of computing the confidence interval so that you can really see that it doesn't matter. As long as you can compute p-values, you can compute confidence intervals. So good luck with the tutorial, and see you soon.